So let's go quickly through what we have seen last week. Essentially, last week we discussed what is called allocation rule. It's a map which takes any game, any TU game, so any transferable utility game, and send it to one point in Rn. So it means to a game you associate how you distribute the utility. The point in Rn means the first coordinate is for player one, the second coordinate is the value of the utility for player two, and so on. That's why I keep R capital N, because it has a meaning, but of course this capital R capital N is the same as R power small n. But here the meaning is, yeah, the first coordinate corresponds to the first player, second coordinate, second player, and so on. So we discussed that last week, some rules, or some allocation rule, and some of their properties. So in order to discuss some properties, I introduced the notion of a null player and what are symmetric players. And I introduced 4 conditions about such allocation rule: the efficient rule, or the NPP, the symmetric and additional rule. And it turns out that there is only one such function which associates to any TU game a point in Rn, which is called the Shapley value, which satisfies these 4 conditions. This is one, if you believe in these 4 conditions, if you're saying that these 4 conditions should be satisfied, then there is only one way to send any game into a point in Rn, or how to distribute the utility. And I was happy yesterday I heard that Shapley value is also used in machine learning. So it has other applications. On the other hand, this Shapley value in general has no relation with the core. The core is something I introduced 2 weeks ago. There is another function phi, which is called the Banzhaf value. It respects 3 of these properties and 1 more, or a different one. And it's also useful for some application. Then we also discuss 2 functions which are even simpler, this equal division value or equal subdivision value. And in order to state the property that these functions satisfy, I had to introduce the notion of nullifying player and nullifying player. And finally, the last part was about the nucleolus. For this, so we take a game, we take a subset, so a coalition, a subset among the player, and any point in Rn. And I've given a definition for the degree of dissatisfaction of S with respect to X. So there was a definition. And you have this for any S. So it means you can generate a very big vector. How many elements of S you have? You have 2 power n elements, or 2 power n subset of capital N. So it means if you take all these values and generate a vector, you have a vector in R power 2 power n. So it means a very big vector. And you put all these dissatisfaction in a decreasing order, or what is non-increasing, but it's the same as decreasing order. So you put these 2 power n numbers in a decreasing order, and then you use the lexicographic order on Rn. And I introduced this last week, which means if you have 2 theta x and a theta y for different point y, you can, with the lexicographic order, say which one is bigger than the other one. So it means you put an ordering on these dissatisfaction vectors in R power 2. And the nucleolus is a point, or is a point X which has a minimum dissatisfaction vector. There was a mistake in the notes, and probably I wrote something also incorrectly on the blackboard last week. I corrected the note, so please check the minimizing the dissatisfaction, what exactly it means. Now it's correct in the notes. And I use this eta of NV. I added this letter because it's more natural. So eta of NV is again a way to associate to any game a point in Rn. It's also an allocation rule. And it turned out that if the core is not empty, then this is inside the core, which is interesting because the core has also good properties. Right. Any question? And last week, by the way, somebody complained about my way of pronouncing the core. No, I don't know. I don't know. But I wrote a second word in French, but I didn't say the meaning. Do you know the meaning of the second word? Yeah, it's a heart. And in fact, it's meaningful that this concept has been borrowed from French because it is the center of everything. You have no one. Okay, let's continue. So we have many things to do. The first thing is related to graph. And in fact, I realized, yes, we could simplify it a little bit, what I'm going to present, but I will tell you more in a second. So this is 5.9. It's called game with communication graph. So we are going to use the graph for modeling communication. Somebody mentioned I could use just a partition. It's true. For what I'm going to present, just a partition would be sufficient. But in fact, people have extended what I'm going to present, and I will say it how, and then graphs are really essential. So it's at the first level, I agree, partition would be sufficient. But if we go one more step, graphs are really useful. So I'm going to call curly L index n. This is a set of graphs. They are simple graph. With n vertices. So what does it mean? You put n points, and of course I'm going to call them 1, 2, 3, 4, 5, 6, 7. So I use the same index as for capital N, and then I put some edges. So this is, and it's a simple graph because we don't have any double edge, so we don't have two edges between two vertices, and we don't have loops. So it's a simple graph. And you observe that, in fact, a graph I introduced in chapter 2 or 3, I wrote it as a pair V, E, V for the set of vertices, E for the set of edges. Here, for today, the V is not really useful. We can forget it simply because V is always going to be n vertices. So if I take a graph in Ln, it's completely defined by this set E. So you will see in the notation, I will keep only E and I will forget V. And this shouldn't be confusing. So these are simple graphs of n vertices. And there is one notion which I need to introduce for graphs, the notion of connected component. So this is a connected component because you can go from one point to another one. This is another connected component. And this is one component. There are maximal components, and this is what I need to introduce, the notion of maximal connected component. These are connected. So connected means you can go from one point to another one. So you have a path. Connected components which are not included in bigger components, which are not included in bigger connected. So let me make this explain the difference. So I'm just explaining what is this word maximal. For example, this is a connected component. These 2 points are connected. But it's not maximal because it's part of something which is connected, which is bigger. So maximal means you cannot extend it further. While just taking these 2 vertices on the edge between, you can extend it to another one. But by the way, you would get the same connected components if you don't have this edge, because you can still go from one point to another one in this component. So as somebody observed, the only thing which is important is a partition, but at a higher level, we can still make a difference. For example, you can consider if this connected component is the same as this one, or if the density of edges play a role, or you can also consider the distance. For example, these 2 points are at a distance 2, while this one is at a distance 1 of everybody. So you have additional structure that I'm not going to use today, but which can be used. And an additional information which can be used is you can also have communication with the direction. So you can also say, oh, this point can communicate with this one. But for example, this one cannot communicate with it. So the theory is richer. We can develop it further. Today, I just consider the fact that this is a connected or maximal connected component. But you can play with additional structure. So what is a TU game with a communication graph? The next definition. So TU game is what we have studied now for 2 weeks. It's a transferable utility game with communication graph. Now you can guess what it is. It is triple. You need 3 information. You have the set N, you have this function V, and you have the set of edges, because as I said, this is the only important information. The width NV TU games, and VE, but I don't write it, a graph of n vertices. I have introduced this set of simple graph with n vertices. And all these triples are denoted by EGL. So the set of all TU games with communication graph are denoted by CGL, communication TU game. Okay. So observe that compared to what we have done up to now, in fact, this is an additional constraint, because up to now, all players could generate coalitions and discuss with everybody. But now I'm going to say, oh, only those in one maximal connected component can communicate. So this guy cannot communicate with anybody else. So it's a new constraint. And just for the notation of an edge, so for I and the 2 players, if there exists an edge in the graph B E between I J, if right. So an edge is denoted by either IJ or JI. There is no difference between these two because it's just the edge. So this one is the edge 2, 3, or 3, 2. The same. I don't put an orientation. We could work with orientation, but it's not useful now. And it means simply that I and J can communicate. We know what is a maximal component, connected component. So I will just call connected coalition. So for S included in N, so the coalition, S is a connected coalition. It corresponds to a maximal connected component. In the graph. So you have the picture. Again, this yellow part is what I would call a connected coalition because we can communicate while this, and it's a maximal one, while these two vertices, it's still a coalition according to what we have done up to now. This is still a coalition, but it's not a maximal connected component. So I wouldn't say that it's a connected coalition. So the yellow one on the picture are connected coalitions. The red one is not, according to this definition. Okay. If you have any question, you ask me. Correlation. You know, if you cannot communicate with anybody, you cannot generate a correlation. So only people who can communicate can create coalition, and I call a connected coalition the maximal one. Okay, that's it. So this is a coalition, but it's not a connected coalition in the sense I have defined because it's not a maximum. And now we are going to do the same game as before. I just use this, we want to define rules which associate to any TU game with a graph, a point in Rn. And I call it phi. So this is what I recall at the beginning. Now we will do it for games with a communication group. So I need to state some properties of this function phi. And again, we will have a theorem saying if you believe in this condition, there is only one way to send any TU game with communication graph to a point in Rn. So I need to state some condition on these allocations group. So this is characterizations of allocation rules. I've presented several over the last 2 or 3 weeks. So the first one is called component efficiency. So a phi which goes from CG of n to Rn, is or satisfies what is called CEFF. We have already seen EFF, but now the C is for communication. If for any remember, this is just a TU game with communication graph. So for if any of them is generated, and any connected coalition S, and the connected coalition is defined here. We have the sum with I in S. I. Remember, phi of NEV is a point in Rn, which tells you what each player is going to receive. So if I look at the entry I of this vector, it gives me what player I will receive. I sum over all players in this coalition, and this should be equal to V of S. We have already seen something of this type, not for each coalition, but for all players. For all players, it was efficiency. So if I forget the C, I just need to do the sum over all I, and I would get V of N. Now it's more precise because it has to be satisfied for each connected coalition. This is a property CEFF. I keep this picture for a second because it's useful. A second property is called fairness. Phi still from T En to Rn satisfies the condition Fn if for any I and j inside N, so for any players I and j, which are connected. So I just write with this. So for example, this 2, 3 is a edge between the two players. One has so phi of n. I will explain. Try to guess the meaning. What does it mean? Phi give you a vector in Rn, you look at the component R. So what the player I would get for this game minus what he would get for the game without being connected to J. So I remove one edge. So for example, I remove this edge, should be equal to what the player J obtained in the initial game minus what this player J get for, again, this game minus this edge. And this is fair because these two guys are connected. So it's just saying that it's fair. This rule is fair if when you remove one edge between I and J, the two players, the difference between what they get with the edge and without this edge is the same. That's the mean. When you see an equation like this, it's often complicated. Try to get an interpretation. An equation is just a very precise mathematical statement, but you should feel it. It's only when you feel the meaning that you understand it. If you just look at this, it doesn't mean so much. If you understand, oh, it means these two guys, if I remove an edge between them or not, they should receive the same thing. So it's fair for both of them. Okay, this is fairness. And the third property is called stability. So phi satisfies this property ST, stability, if for any game NVP, so it's a game with communication graph, then Ij in players linked by an edge, one hat phi of NVP. They are very, very close, these two properties. It said that just for player I, being in the graph with the edge give you a better value or give you a better outcome than if there is not this edge. And the same for J. And so the similar statement for J. So it's not the direct relation between these two players, but it says for player I being in the game with the edge Ij is better than without. And the same for player J, being in the game with the edge between I and J is better than without. That's called the stability. So it's again, this edge can only give you an additional gain. So now I have these three properties for phi. I have given a name for these three properties. I can soon give a theorem using these three properties or these three characterizations. I just need one more information. Since only connected coalitions matter, I told you only the maximal connected coalition important. I'm going to define a new object for NV here. Define the games NV. It is just a new game. So look, I'm going to from a game with a communication graph, I'm going to define just one game. So I lose the structure of this communication graph, but it's probably is related to the fact that I'm only using the partition. So how I define this NVE, defined for any S included in N by, remember, for TU game, I need to define this for any coalition, not only for the maximal connected one. And how I define this, I just take the sum over all coalitions in S, R, connected conditions of, let me, my picture is not too simple. What does it mean? Suppose this is a graph. We have four maximal connected components. I want to take any S and define VE of S. I take all connected coalition inside S. So suppose if I take S, that's easy. I sum the V of this coalition and the V of this one. If I take V like this, it contains still and only two connected coalitions. So it's the same value. And the same if I do this, it's still the same number. While if now I take this one, there is a new connected coalition inside. So the VE for this S takes into account the three connected coalition. Okay, that's it. So I define a utility for a V of a function V on all subset of N by just summing over the connected coalition. And now you observe, I don't need the graph structure anymore. Everything is encoded into this function VE. Definition, and then the theorem definition. It's called the Meyer-Sum. Meyer-Sum value by n from the set of it's a function from a set of communication of TU game with communication graph to Rn is defined for any and then what does it mean? You need to remember what is the right-hand side. Last week I introduced, and I'll just recall it at the beginning, this is a Shapley value. It has a complicated definition, but it has also nice properties I mentioned last week. And the Shapley value was indeed defined for a TU game. And now I define this new function defined on any TU game with communication graph as a Shapley value, which was defined last week, of this thing I just defined. So everything is well defined. This was defined last week. This is just defined for any TU game with communication graph, and I give these definitions. You can be lazy. The right-hand side is well defined. You give your name, put your name instead of M, and the definition is fine. And what is the theorem now? That this is the best solution. Theorem. This Meyer-Sum value from all TU game with communication graph to Rn is a unique. It's a unique allocation rule. which satisfies CEFF, which is efficient for all coalitions or for all connected coalition, and it satisfies a fairness condition. And there is one more sentence. If the game is super additive, I didn't emphasize it so much, but in fact, most of the game are super additive. Then M is or satisfies this stability condition. So how should you remember this? We introduce an additional structure, which is this graph. So it means communication is not between everybody, but only in the connected component. And we consider only the maximal connected component. I define in this setting what is CEFF, FF, FN, and ST. I just define this Meyerson value, which is based on Shapley. Shapley is important. I already mentioned at the beginning, it even appears in machine learning. So and if you look at the definition, it's something rather complicated, but it means it contains some information. So you define this new value based on Shapley value and this notion of games I have just introduced here. And you get that the only way to associate the value for all players to any TU game with communication graph, which is efficient in this sense and fair, is by using this value. Okay. Is there any question or remark? So now we are going to start the last chapter, which is essentially a list of applications, a list of examples. But sometimes I need to add a bit of theory. I will present several examples today and next week. So this is chapter 6, the last one. I call it applications. And the first short section is it's essentially an observation or a remark. Cost. Especially if you look in the literature, sometimes these games are for getting something. So this is a utility game, you get something. Sometimes you do a coalition in order to share the price of something. So if you have to buy something, and if you are 2 persons to buy it, or if you are 5 persons to buy the same object, probably the 5 persons would spend less, or each person which spend less will spend less. And so this is more related to cost game. So it's not always you win something, sometimes you lose less by doing coalition. So it's essentially the opposite. So let me just write a few sentences about this. So far, what I call V of S was interpreted as a gain or something you get as a benefit for coalition tests. As I said, often the cost appears instead of the benefit. It depends what you are going to model. But you have to be careful the letter you use. So for benefit, I use V. For cost, we will use C of S. C is for the cost for coalition. And then you have two possibilities or two approaches. Either whenever you have a cost, you take the negative, and the negative is going to be a benefit. So two approaches for dealing with this problem. The first one is translate any cost gain into a utility gain. I'm very vague, but I just want to warn you about what you can see in the literature. So you transform a cost gain into a utility gain, and then you study. So it means you go from C to a V. You study the utility gain with what we have done so far. Study the utility gain and translate again into a cost name. Translate again. This is a bit stupid because you start with something, you translate it with some dictionary, you use what we have developed, and you translate it back. So this is not the best approach. It works for some games, but it's better to do the theory we have just developed exactly in the same way, but for cost gain. So you start from scratch, and so this is the second approach. Develop the entire theory of chapters 5, because this is where we deal with this for cost gain. For futility. So it means you do again the entire program. Of course, I'm not going to do it, and you are probably not going to do it, but this is much better. And what does it mean essentially? Whenever you have an inequality in one direction, essentially you reverse this inequality. I cannot promise that it works, but essentially it's what you have to do. It means reverse inequalities. And modify slightly some definition. As I said, I'm not going to do it, but from the point of view of the beauty of mathematics, it's better to do this approach because it's not just a translation, is you do the theory really for cost gain and not only for utility gain. And when I say you modify slightly some definition I have written in the notes, you have to modify a little bit what is now the set of imputations for the cost gain. I gave a definition, of course you need to modify it. I gave a definition for the cost of a utility gain, so you need to change it for now the cost gain, but nothing is very different. And in the application, you will see that we don't have to think so much. In the application, we will sometimes see a cost gain and things are natural. But I wanted to stress that there are these two approaches. It would be better to do this one, or it's better to do this one, but you need to modify a little bit. Okay, that's all what I wanted to say for this section. But yeah, don't be surprised if somewhere you find cost game instead of utility games and with some inequalities in the other direction compared to what I said last. Airport problem. Airport game. So this is a very practical problem. This is a runway where airplanes are going to depart or to land, to take off or to land. And it's divided into different pieces. I call it this C1. This is C1 is this. C2 is going to be this part. C3 is going to be this part, and C4. I will explain this. What is the problem? You have different airplanes. Big ones, and you have small. These are airplanes, in case you don't recognize. And you have a certain number of these airplanes taking off or landing on this runway, the same for this and the same for this one. But of course, for this one, I need a 4 because they are very tiny. For the smallest one, this length would be sufficient. For the middle one, you need a bigger runway. For the third one, a bigger one. And for the fourth one, you need the entire runway. So the question C represents the cost for building this. The C2 is for building this part, C3 for building this, and C4 is the cost for this. And the question is, how do you assign a price for each airplane about a price for landing and taking off? This is a very practical problem. And which runway do you construct? For example, if you only have these 3 types of airplanes, you don't need the biggest part. So you have also to adapt the length according to the size of the airplane. And how do you distribute the cost? So I will write the framework, and then we translate it into a game theory problem, and I will state the result with what we have there. So the problem is we have M types of airplanes. In this example, I draw 4. And for type L, so let's say L is this one, or one of them. So L is between 1 and M, because you have M type. For type L, we have what is called NN. It's called a movement. What does it mean? This is takeoff and landing. So a movement is either when an airplane takes off or when it lands. So you have this number, I don't know, during 1 year or during 1 month, you have this number of landing and taking off for the type L. And the cost of runway is for airplane of type L is CL, and this corresponds to my picture. So this is 1, 2, 3, 4. Then for the smallest one, you need this length of a runway for C2, C3, C4. So we have these different, this is the ingredient. NL movement for type L of airplane, and the cost for the corresponding runway is CL. Yes?
You're supposed to mean like the maintenance cost, right? Not the construction cost, because if you don't construct the runway big enough, those planes can't land.
It depends if you want to build a new airport or if you are just maintaining or keeping one airport. Doesn't matter, it's not an important question. Maintenance or construction, what's the big difference? Of course, it's probably big. The amount is probably very different, but for my problem, it doesn't matter if you start from zero with no runway and you construct it, or if it exists and you just pay for the maintenance. Doesn't change anything. Okay. So the question is who is going to pay the bill? Who is going to pay for this? So who pay for? Oh, more precisely, how much? How much for each movement of airplanes? And we have to be a bit fair, because if we have only this type of airplane, we don't need this big runway. So the cost will not be the same for all of them. So we have to transform this into an airport bay. I need to translate this problem into an airport bay. So NL, so you can already guess a player here is either a landing for plane of type L or a takeoff. So because this is a movement, you want to know how much it costs for each movement. So one movement is either taking off or landing. So the NL is set of NL players of type L. So it represents for each of them, you have one movement. And what is the total number of players here? It's a union over all types of airplane. Because this is the cardinality of this set is exactly how many planes took off or landed on this runway during 1 year. What is S? S is any subset of N, as we have seen. And I'm going now to set the V of S. What is the cost for coalition? Now you need to think for a second. Coalition is, let's say, 3 landing of this type of airplane and 2 taking off of another type, for example. So, or it is the movement for one company. One company has different airplanes, they take off, they land, and so on. So it's minus the maximum of CL. Please try to think about this. What does it mean? Because, as I said already, if you have only small airplanes, there is no reason to pay for long runway because you don't use it. So the cost for the coalition, you look at the biggest L, so that you have an airplane of this. So you look at, in S, you look at the different types of airplane. and take the biggest one, and it corresponds to the biggest cost. Why is it natural? Because if you have one airplane of this type, then these two can still land on the runway for this one. But if you don't have of this type and only have of this one, you don't want to pay for the runway of this one. So think about it. You look for the longest or the biggest airplane you have, and you are going to pay only for the runway corresponding to this size. Yes. Is it a good question?
It is okay. So I was gonna say, should we multiply it by n simple n?
No, wait a second. I'm just setting the framework.
Well, simple n, right?
Indeed, you want to take a kind of multiplicity, but I'm not at this point yet. I just give a rule. And now we call n with this b, this is called the airport gate. And there is an exercise in the note, and I need to introduce one definition. MV is convex. I haven't introduced this notion of convex for a TU game, so I need to say what is convex in this framework. Namely, so I just write what is the notion of convex, and then you will see that it's a useful notion. It's convex is for any I in N, any S and T inside N minus I with this is a definition of convex in this setting. It says if you have, I mean, it has nothing to do with the airport game, but it turned out that the airport game is convex. If you have two subset, one or two coalition, one into the other one, V of S union I minus U of S is smaller than V of T union I minus V of T. This is a definition of convex in this set. And I did not introduce it before. I could have done it, but I didn't do it. But convex games have a good property. So let me just state this good property, because as I said, this one, it's an exercise to show that it's convex. Again, this is a slightly abstract lemma. I'm still looking at this, but of course it doesn't mean anything. Any convex game or any convex TU game satisfies so this is a good property. It says that if you are dealing with convex games, the core is not empty, and what I define the Shapley value is inside the core. So it means if you know that your game is convex, this set which I introduced 2 weeks ago is not empty. And in addition, what I introduced last week is inside. This is true for any convex game. So in particular, it's true for this one. So what is the solution for this problem? I just need, in fact, the solution quite pleasantly is going to be expressed in terms of the Shapley. Shapley value, but it will have a good interpretation. I just need to introduce two things before I state the statement. I'm going to set R index L as a sum of N D. I can write small. What is this number L or any L? L is inside one, and fix the size of an airplane and count how many airplanes or how many movements you have of planes of the size L up to the biggest size. So if L is this one, I'm counting how many movements I have for planes of this size, and this size. The sum of the movements of planes from size L up to the biggest one. So this is just a definition. And I also introduce C0 is 0 simply because I'm going to give a formula with C1, C2, C3, and C0 will appear naturally. So this is just an orientation. And I want to keep this picture. So convex game, I gave the definition. It is next. So what is the solution of this problem? And you will see that it's perfectly normal. So theorem. For the airport game, B in for any player I of so the player is a movement, remember, of one plane. So it's of plane of size. Let's say this one. How much is this going to pay? Pi of S for this game is going to be minus the sum L from 1 up to N. So let's try to understand this formula and see that it's perfectly fair. This first part has to be paid by everybody because everybody is using this first part. So I take each plane is going to pay C1 minus 0 divided by the total number of movement. So if we had 100 landing and takeoff, it's this price divided by 100. But now the second part, or the difference between what has to be paid for this one and what has to be paid for this second part, has to be paid no more by the first one because they don't need it, but by all the other one. So for all the other one, they have to pay the difference between C2 and C1 divided by all airplanes or all movements of this type. And now for the bigger, those one of this side, they need this additional part. For this one or this one, they need this additional part. So they are going to pay the difference between C3 and C2 divided by the number of movement of these airplanes and so on. So it's a very fair way of distributing the cost for this problem. And because it's the Shapley value, remember, we know that this solution has 4 properties. One is it is efficient. The second one doesn't mean so much. It was about null player. So if somebody doesn't fly at all, this person has not to pay anything. This is probably correct. And there are two additional properties. The symmetry. Symmetry means two planes of this type have to pay the same thing, which again is completely fair. And there is a fourth condition about the additivity. So this solution which appears, if you do the computation, it's really what you obtain, is indeed a good, fair solution for this problem. But of course, there also exist other ways to distribute the cost among all players. This is one solution, and it respects these four conditions. Okay, so this is an application of what we have seen. By the way, the convexity is not really used in this statement, but it turns out since the game is convex, we know that this solution is even inside the core, so no coalition would complain about this. It's the property of the core. Any question or remark? Yes.
This seems similar to when you have a group of friends eat at a restaurant and one person only eats salad.
I'm sure you have plenty of equivalent problems. You can restate this in plenty of equivalent. Translate into different languages, I'm sure. But this, you cannot write a report about just a translation of this problem into something at a restaurant. This is not enough. Yes.
So the Shapley value is what each player I should pay, right?
A player is here, one plane taking off or landing.
Yeah, so the Shapley value is what each player should pay, right?
Yes.
And is that N or R?
Divided by R.
Yeah.
R.
So that's the number of movements, right?
Bigger than, so for if L is 2, it's the number of taking off and landing of planes of this type, and this.
So like it's in the denominator, but like if a player makes more movement, shouldn't they pay more?
Yeah, but each time this is per movement. Each player, a player is one movement. So if one, it's not per plane or per airplane. If one airplane lands 20 times, they will pay 20 times this. It's per movement. So one movement is a player in this case.
Okay.
It's not one airplane. Otherwise, I would have to, but it would be more complicated because each airplane would have a multiplicity. So here I just count one landing or one taking off as a movement or as a player. 6.3. Bankruptcy. And again, I'm sure you can translate this into very different problems. What happens here? We have N players or N claimers or L players claiming for a portion or for something for a portion of resources bigger than the one available. This is the idea, bigger than the one available. Why is it called bankruptcy problem? Simply because after bankrupt, you have just one estate, so the company has only one something amount of money or some building, and there are different persons who are claiming for their value or for some money, and they are claiming for more than what is available. So again, you can translate this in for different examples. So let me be more precise. It's when the resource is not sufficient according to all planes. So definition. the bankrupt person. It's N. Be careful, this E has nothing to do with the E I mentioned before. I will explain here. E is just one number. So with N players, always E is a number, a real number, which is called the estate, which means what, or the resource, what is available. Money available. MD now is a vector in Rn because it corresponds to each di is bigger or equal to 0 and 0. So D is what a player I is claiming. So DI is a claim. So what he would like to get, the problem is that if you sum what all players would like to get, it's more or equal, but the problem is when it's strictly more than what is available. So how are you going to distribute what is available among people which are claiming for more? It's a natural problem. And again, this is a problem. We can translate this into a game problem or transferable utility game. So the bankrupt game is of course just NV, and I need to say who is V. Is V. V of S I define as a maximum between 0 and E. So I take for coalition, I've written in the notes, it's a pessimistic approach because coalition S would like to get E minus what has already been claimed by the other one, the one not in the coalition. But of course, if this number is negative, you don't want to claim something which is negative, so you put the maximum between 0 and this. So as long as this one is positive, of course, this is the value, but if suddenly it becomes negative, you take C. Again, there is an exercise because it's useful. This game is convex. We know that the core is not empty and that the Shapley value is inside. So what we want to do, we want to have rules for distributing the money. How to distribute this E among the N players. It's a very practical problem. And this is called a division rule. Division rule. It corresponds to an allocation rule. Is a function that I denoted by F, which take any so it takes any bankruptcy problem and send it to a point in Rn, which is what each player will get. This is any. Right? So I want to have such a rule, and of course this F is not unique, but it has to satisfy a few things. If I look at what player I get, this is the entry I of this vector, and if I sum up over all players, I should get E, because the total amount should be distributed. And there is a second thing, 0. What does it mean? It means no player should get more than what they claim. The player I would like to get DI, this number, he will get something which is between 0 and what he claims. He cannot get more. That's the two rules that a division rule has to satisfy. It's a function from any bankruptcy problem to Rn, dividing the total amount of the estate between all players, but no one should get more than what they claim. Do you have any questions? Okay, so there are different rules. And maybe I will present them in a different order. I don't think I will be able to do all of them. So let's start. I do it in a different order. The easiest one is called the proportional rule. It's not in the same order I in the notes, but at least we understand this one easily. So f of, I call it PR for proportional, of n dv. So you're going to receive something which is proportional to what you want. So this is the simplest one. You take di divided by the sum of dj. This is quite clear. Each person will get something which is a ratio between what this person claimed and all the claims multiplied by E. So you can check if you sum these values, of course you get just E, and this is always smaller or equal to 1, so you cannot get more. If all dj are 0, Evido, you haven't mentioned it yet. If all dj are 0, it's not meaningful, but it means nobody is claiming anything, so you don't need to take care of this situation. You don't need to take care of this situation.
This PR.
Sorry?
PR.
Proportion. So this is the simplest rule. But I'm not claiming that it's the most interesting one. So let's go to something a bit more complicated. Okay. Let's go to number 2, which is constraint equal. This is still not too difficult. So each claimant, so each player, in this case our claimant, they claim something, receive the same amount. So they all receive the same amount, but with one condition. Conditional. No one receive more than his claim. And this is part of this condition. Nobody should receive more than what this person claimed. So we want to give the same amount to everybody, but nobody should receive more than what they claim. So how can I encode this in one function f, one division rule? It's not so difficult. So this is called f CEA for constraint equal award of n B for player I. Player I should receive the minimum between bi and lambda. And I have a condition to write on lambda. With lambda, as we will understand, with lambda satisfying that the sum over I of minimum of bi lambda is. What does it mean? It's not so difficult to understand. We want to give the same to everybody. And the same means this lambda. But if this lambda is for one player is bigger than its claim, we don't give more than the claim. So we want to give lambda to everybody, but if this lambda is bigger, we give just di. But since we have to distribute the entire money, it means that we will fix lambda so that when we do this sum among all players, we have to get. So if you try to solve this problem, probably what you have to do, you have to increase lambda, let's say from 0 up to a certain number. And each time you meet a certain di, you have to be careful, I let you think how to implement this. So take a certain number of di, and you can implement this. This is called the constraint equal award. And then probably the last one for today, which is of the same type. It's common. I kept the most difficult for next week. This is called constraint equal losses. So now the difference, what is the idea? The difference between the claim and what each player gets, and what each player gets should be constant. Now it is this difference which should be constant or should be equal, but again conditional to something. Conditional then it is not less than 0, which is a bit stupid, but indeed nobody wants to get a negative number because we would have to pay. So how to encode this in one function which is not so different. It's the same idea as the other one. So f CEL of n d for player I is now the maximum between 0 di minus 1. And indeed, so as long as this number is bigger than 0, it is this number which wins. When it's 0, it is this. When it's negative, it is this one. So you want to have the difference between what each player claims and what they receive. This difference should be constant. But lambda has to satisfy again a condition with lambda satisfying that again the sum over all I of these maximum has to be equal to E because you want to distribute the entire amount. So again, if you want to implement this, how you do it, you should start with a certain lambda, and whenever you reach a certain number, di, you have to be a bit careful. There are two more ways to distribute this money. One is called the random arrival, and the other one is a contested garment rule. I will present them next week. They are a bit more complicated, but please keep in mind the framework. Oh, by the way, yeah, I said next week is optional, so do whatever you want. But if you want to know another solution, which is even more interesting, I encourage you to come. Otherwise, you would never know it. And I will finish with a few additional examples and probably one from biology and chart. Okay, so that's it for today. I finish early.